I welcome Mike Meriton, co-founder and COO for the EDM Council. Mike.
Thanks, Carol, and welcome everyone. So why are we all on this webinar? Data sets are growing exponentially, and with the advent of alternative and data and the cloud, this is even a growing issue. This is further compounded with regulation and risk requirements, making data and risk analytic programs struggle to keep pace. In the middle of the pandemic, companies are now challenged to make trusted decisions on solid data so they can rapidly adapt their business models, and the stakes have risen in a big way on this problem. In this EDM webinar, we are going to explore risk analytics using knowledge graphs, FIBO, with deep learning. I'd like to now introduce our two speakers, Thomas Cook, Director of Sales at Cambridge Semantics, and Greg Steck, the Director of Data Engineering at FI Consulting. Thomas has a master's in computer science from Texas State University and brings 20 years of experience in software engineering, ETL, data warehousing, and big data. And prior to joining Cambridge Semantics, a very long-term EDM Council firm, Thomas worked at both SAS, IBM, Netezza, and Talend. Greg Steck is the Director of FI Consulting data engineering practice that helps financial institutions understand their complex data problems and develop solutions to optimize performance and costs. Greg leads technical teams to develop and implement cloud solutions in the areas of portfolio, credit risk management, model risk management, stress testing, and risk analytics. Greg holds an MBA from Thunderbird School of Global Management. So welcome, Greg. Good to have you join us. I let the discussion go over to you.
Thanks, Mike. Yeah, we're excited today to talk about knowledge graph with FIBO and a deep learning exercise that we're going to go through. So Gartner reported recently that close to 50% of AI and machine learning projects fail in part due to challenges with data complexity and systems integration. So today we want to talk about some of those data challenges and how a knowledge graph can help address them. So three key challenges that we see financial institutions face related to data complexity and systems integration are: one, integrating data from disparate data silos; two, staging data for analytics when business requirements are changing frequently; and three, capturing data provenance throughout the analytics pipeline. So we're going to demonstrate that addressing these challenges using a knowledge graph can provide some significant advantages over a typical relational database approach. Specifically, with a knowledge graph, we can natively capture detailed data lineage for regulatory compliance, meaning we don't need a separate data store to manage the metadata. We can reduce time spent on data engineering tasks by over 50% by creating a flexible and reusable data model. We can overcome some limitations of machine learning because machine learning algorithms blindly search for the strongest signals in data, whereas a knowledge graph can provide context to these signals through semantics. We can enable self-service by connecting business terms to data elements, so we'll talk about how an ontology helps with that. And we can turn complex domain knowledge that resides with experts into explicit knowledge stored in a graph database. So knowledge graphs can add value to many different use cases for financial institutions, including risk analytics, model risk management, customer 360, AML, and fraud detection. The focus of this webinar will be on risk analytics, but because we'll talk in depth about some of the data engineering challenges around machine learning and AI, the concept should apply to those other use cases as well. So as we talk about this use case, we're going to go through a case study using Fannie Mae public data to build a deep learning model. So Fannie Mae provides single-family mortgage data that has about 40 million loans over 20 years. So that's about 2 billion monthly observations that we can use for our deep learning model. So we're going to take that loan data and combine it with unemployment rate data and house price index data that we source from the FRED database. The FRED database is a great resource for economic data and is provided by the Federal Reserve Bank of St. Louis. Lastly, we'll take some COVID data to layer on top of our model outputs. Before diving into some knowledge graph concepts, we're going to talk a little more about some of the business problems that we've seen for risk analytics. The first one we mentioned is integrating internal and external disparate data sets. So the idea is that data scientists and analysts spend most of their time on data prep rather than on generating insights. In our example, we had to take the loan data from the Fannie Mae system and combine it with the Fred API data. One of our main challenges was being able to consistently join data on geographic identifiers. So we'll talk a little more in depth about that. The next problem is tracking how data moves and transforms from the source system to the end data product. So there are several people in an organization that are challenged by the lack of data provenance. We've just listed 3 examples here. The first is a modeling team that manually captures and manages source to target mappings to track data lineage to comply with BCBS 239. The next is a developer who doesn't have full visibility to downstream data dependencies when making application changes. So that can have several effects, including delaying the release or releasing a breaking change that significantly impacts another team downstream. The last one is a business analyst who spends hours tracking which input files were used to generate an analysis just to field an internal audit request. So on the right here, we have a snapshot of a tool that we're going to look at the end called Solidatus, which basically gives us a visual way to see the data lineage we captured in the knowledge graph, from the source data all the way to our regulatory report. So another problem is staging analytics-ready data for frequently changing business requirements. So in our example, we have our source data on the left, the loan performance data, the acquisition, and the macroeconomic data that comes from the FRED database. We need to get all that data and get it ready to put into the deep learning model. In order to get it to that state, we have to create a complex ETL process with lots of business logic. So an example of this is an IT support team that spends months developing an ETL process to meet specific requirements, but then every month or every quarter, when regulators or senior management want to see something different, the team needs to go back and revisit this ETL process. And maybe the original developer has left the company and a new person needs to take it on, and it just becomes this very complex thing that takes a lot of time and money to maintain. So here are some other problems that we won't talk in detail about today, but a knowledge graph can also address them. Lack of common data fields and schemas, which increases the overhead of sharing and consuming data with other teams. Another is producing and maintaining quality model risk management data at a low cost. So model risk management data is challenging because it typically spans multiple silos across the org, and maintaining the data in a cost-effective way can be challenging. Long throughput time to generate analytics. So this is more from an operational perspective. It just takes a long time to generate that data. And finally, a complex IT infrastructure to produce and execute models. So as we look at some examples of how a knowledge graph can add value, we're going to go through what we think of as a typical risk analytics pipeline, and we'll compare and contrast the relational and graph approaches. So for those less technical folks we have on the call, we'll come back to some of the business value at each step in the pipeline. So the first step in our risk analytics pipeline is designing the data model. So for designing a data model for a relational database, let's look at our simple example here. We have our loan table on the left, our property table, and then we have our monthly snapshot. So every month when the borrower pays down their loan balance, we have a snapshot that captures how much they paid, what the new loan balance is, and then we have the life cycle status field that shows if they're current on their loan, if they're delinquent, or if they prepaid. And then on the right, we have the FRED data, which we have quarterly and monthly data, potentially in different tables. The last thing here is the COVID data on the right. So the COVID data that we have is captured at the FIPS level or the county level, and we need to take that county level data and aggregate it up to the metropolitan statistical area, which is a broader geographic area. So that will usually involve a crosswalk table. So for small data, this will be okay, but when we try to scale to larger data sets, these joins will be time consuming. So one challenge is all the joins that we'll need to do at query time, but the other is the lack of context in this model. So because relationships can't be labeled directly in the model, it can be challenging for someone to understand which business concepts the data is capturing. Okay, so for designing a data model for the graph database, we'll first focus in on the loan data and then expand to the rest of our example. So for this data, we can leverage the FIBO ontology. So using an ontology will speed delivery because we can reuse a lot of the schema that has already been developed. It will promote consistency across teams since we can align on specific terms for what a mortgage loan is, for example. And it will encourage interoperability between departments since when I give this team the data I've generated, they'll be expecting the same date formats and loan terms. So we have in our example these terms from the FIBO ontology. A loan application may become a mortgage loan. A mortgage loan contract sets out the terms for a loan has a snapshot, and a loan is collateralized by a property. So one thing we found with the use of ontology is that we're able to capture a lot of the domain knowledge. So it may not be as apparent here, but with one of our clients, we were trying to model loan accounting rules, which can be very complex. A loan can fall under multiple accounting treatments, for example. And being able to codify that in the data model, we felt like it really captured some key domain knowledge that otherwise would reside with a few key people on the team. So in other words, it turned tacit knowledge into explicit knowledge for the team. And as we mentioned before, it's very difficult to express that type of domain knowledge in a relational database, primarily because we can't label relationships between data elements like we can in a graph. So this is our data model kind of zoomed out and simplified a little bit. We still have our mortgage loan and we still have a snapshot of them up here. And we have our property collateral and we see that it's identified by our MSA. So this is our geographic identifier. So this is where we connect our data silos and where we link the macroeconomic data. Another thing to note about this design is our joins are determined at design time rather than at query time. So what we mean is that when we design the ontology, we explicitly state how entities are related, in contrast to a relational approach where at query time, we need to understand which tables should be joined and how they should be joined together. So we're going to take a quick look at the FRED data to see how we can represent it in a graph and how we can link it to the loan data. So to set up the problem, let's quickly look at how the FRED data is organized. FRED has an API endpoint that returns category IDs along with its parent category ID. So we can take this and we can dump it into our graph and we can see how the categories are related. So at the top, there is the root category, which has no name, and then you have several categories, including prices and US regional data. We use the SCOS ontology to organize the categories, and the broader predicate here shows the relationship to the parent category. Under regional data, you have a subcategory of states, and under states, you have all the different states. In our case, we're looking at Wisconsin, and then you have an MSA category, and then finally an Appleton, Wisconsin category. On the prices category, we have a subcategory of house price index. Now, FRED has another API endpoint that gives us the economic series data. In addition to the time series data, we get which categories the series are organized under. So the HPI and unemployment rate series data are categorized under the house price index and the Appleton, Wisconsin category. We use the term theme from the data catalog ontology, or DCAT, to describe the relationship between the series node and the category node. So the HPI series is also categorized under the Appleton, Wisconsin category here. So if we were to model this structure in a relational database, we would need to have a self-join on the FRED category table, like you see here on the left, because the parent ID refers to another category in the table. So if we wanted to query for all of the series under the prices category, we would need to write a more complex SQL query with self-joins compared to a simple query in the graph database where we would ask for all the nodes under the prices category. Okay, so now let's bring in the loan data. So we put the FRED data on the left, we have our HPI and unemployment shown, but also note that there are several other indicators that are linked in the same way to the Appleton, Wisconsin category. For our loan data, we have our loan, our property, and the MSA that the property is located in. The problem is that the MSA ID we have of 11540 does not exist in the FRED data. The FRED category just has the name of Appleton, Wisconsin. We also have an MSA label in the loan data, so we can join our link our data on that text field. So, but the challenge is that not all the MSAs match up exactly that way. For example, San Antonio, Texas has New Braunfels in the MSA label, and it does not have it in the FRED data. So we'll have to have some special handling for those instances to make sure that they are linked correctly. In our case, we did some simple fuzzy matching to get the link correct. If we did this with a relational table, we would still have the same issue, but not a clean way to save our logic for the join without creating a new table or altering the data sets. Now, when another team comes along and wants to do this, they'll have to figure out how these entities are related if they join the two tables again. And what's worse, maybe they don't realize that the whole column doesn't join as easily as Appleton, Wisconsin, and they report incorrect data. So if we do this in a graph, we can create that link and document it in the graph how it was created so that the next person or team doesn't have to redo that same work. And we didn't structurally modify either data set. So this is what we mean when joins are determined at design time rather than query time. So this idea is really important in other areas like master entity management and entity resolution, where we can apply more advanced natural language processing techniques to create links between those nodes, and where we might want to assign different weightings to links between entities. Now that we made that connection, that now exposes all the other metrics that are linked to the FRED category to our loan data. And we can easily traverse the graph from the loan all the way to get any of these metrics that we'd want to build a model. So that means that data scientists and modelers spend significantly less time wrangling data to combine macroeconomic data with the loan data. That also means that other third-party data that is used widely in the organization can be correctly linked with internal data once and then reused by other departments. So here's an example of what our Sparkle query looks like to join the FRED and the loan data. And we won't talk about the syntax, but you can see in a relatively few amount of lines of code how we can get our loan data. We can traverse from our MSA to the series name, and then we can pull the data from the series. So we can easily swap out or add additional data series to this query, and Ansel Graph can execute this query at scale. So the next section is ingesting and storing the data. So the comparison between graph and relational approaches in this context is challenging because it can vary greatly depending on tooling. So our focus will be on a couple challenges associated with integrating the data from the FRED API into the graph database, but this is a much bigger topic that we won't try and cover here. So from a relational approach, we would have to create a Python script to call the API to return that JSON data, and then we would have to convert the JSON object into a relational format and store it into a database. So there's just a lot of overhead with getting that data and putting it into the database. Now with a graph approach, this is much easier in part because Ansel Graph has a built-in feature to schedule and call the API directly, and then we can save the JSON object in Ansel Graph. The graph model better accommodates structured and semi-structured data than a relational table because in a relational table, we might have to flatten that object to get it to fit into a table. Using a framework like JSON LD, we can store the JSON object as is, much like you could in other NoSQL stores like MongoDB. So this just makes it much faster to ingest data because we have a lot of flexibility in how the data is input. However, having a flexible model is a double-edged sword, and we would also need to make sure that the data quality is good. So for that, we can use the shapes and constraints language, or shackle, to validate the graph, the shape of the graph. So that gives us a good tool to create unit tests and other validations for the graph data that we're generating. The next section we're going to talk about is staging the data for analytics and modeling. So typically when we stage our data, especially when it's large data, we need to denormalize that data into one table to improve query speed. So similar to what we talked about before, we have to take all these tables and combine them into one table, and that creates an ETL process that's difficult to maintain. Additionally, when we create an ETL process, we'll want to capture the metadata information associated with that process, for example, a source to target mapping. So this is typically done manually, or it relies on an external application to parse SQL code to get the source to target mapping, but either way, it will end up in another silo separate from the data it's describing, which makes that data more difficult to use. And finally, the last issue is that when our team develops this process, they develop it for a specific requirement. And then they have another requirement that comes from the business that's similar, but slightly different. So they have to create another table for that and so on. In the end, you have multiple tables for similar use cases, and that creates a risk for data duplication and data inconsistencies, when you report internally or to the regulators. So we've seen this as a problem at many of our clients where there are challenges to maintain kind of a golden record of data to report on. In contrast with our graph approach, our data does not need to be denormalized. We found that with ANSOGraph, joins perform very efficiently without any of this type of denormalization at scale. Because we don't have to denormalize, the only part of the ETL process that is left is the low-level calculations, and those can be reused. Because the graph we developed can be reused across different use cases, we can achieve economies of scale in a sense because the marginal cost to add a new use case decreases, and we can share the data management and maintenance costs across multiple cost centers. So going back to our example of staging data, another benefit is our ability in the graph to directly attach metadata to the calculated field. So the nature of the graph data model allows us to describe data lineage at the same time we create a new data element. So this example, we wanted to calculate a loan age, and when we ran this calculation, we were able to link the provenance information directly to that data point. So we can say that a snapshot has a loan age of 3 years, and that data point was generated by microservice 123, and then we have some runtime information about that microservice. So this is what the query looks like when we run the calculation in the graph. We have the calculation in the where statement, and then in the insert statement, we can add a part to track the provenance. In practice, we would embed this in the Python code and automatically capture info about the microservice that executed the code. Now, for data steps outside of the graph, we can still capture that information automatically. For one of our clients, we developed a set of Python decorators that could be integrated into the PySpark code that captured this level of detailed data, data lineage, and sent it to the Knowledge Graph API. So the next stage is training the neural network model. So in our graph, we have all the information we need to train a model. We have some X variables on the mortgage loan contract, including FICO score and loan origination amount. We have the macroeconomic variables on the bottom right. And then the Y variable that we're trying to predict is on the snapshot node. So for every snapshot in the future, we want to predict the next loan state, if it's going to be delinquent or if it's going to prepay, etc. So this was the fun part where we got to spin up a large cluster and put the database through its paces. We created one large distributed graph in ANSOGraph with about 1 terabyte of data and 49 billion triples, and then queried the training data to feed it into a framework for deep learning called TensorFlow. So we have some quick stats on the process here on the right, but we were impressed with the speed of ANSOGraph, especially given some of the complex queries and calculations we did. So from a business perspective, faster execution enables us to do more iterations of our stress scenarios or our forecast scenarios and gets the insights faster, all while maintaining a flexible, reusable model that we can quickly update and track data lineage along the way. With a fully denormalized relational table, we might be able to achieve similar performance in terms of speed, but the trade-off is we lose the flexibility and the reusability. With the graph, we can have both the speed and the flexibility. So to train this model, we still had to take the data out of the graph and put it into a TensorFlow model that took the input as a matrix. Now, another approach to this is to use knowledge graph embeddings and graph neural networks. So knowledge graph embeddings are a dimensionality reduction technique that encodes information about a particular node into a vector. We can use a graph neural network approach directly on the graph and gradually change a node's embeddings so that it can accumulate information about neighboring nodes. So in this case, our MSA node can have an embedding that has information about several different macroeconomic series that it's connected to. Then we could use that single MSA embedding as an input to our predictive model. We could also have a mortgage loan contract embedding that encodes information about the borrower FICO score, the origination amount, and other attributes that were collected at the time of origination, and use that embedding as an input to our predictive model. So we've started to work more with these graph embeddings. We see a lot of business benefits because we can simplify the feature engineering process, we can bring the model training closer to the graph, and we can leverage some of the semantics and other relationships that we've modeled into our graph data. So now that we have our model trained, we can start to build our forecast scenarios and create an output report. For our relational approach, we will need to add new tables to capture our regulatory and internal stress scenarios. So our FRED data here is the historical data, and now we'll need to add the forecast scenarios or the stress scenarios into the model prediction. Ideally, all of these scenarios would be in the same table, but given that all these scenarios typically come from different parts of the organization, it's more likely that they're in separate tables and even separate databases. So looking at the graph approach, we can see an example of being able to quickly extend our existing data model. So in our example, we have the MSA that has the house price index data set, and then we have our historical observations that came from FRED. Here I've just illustrated them in a tabular format, but we're basically capturing the date, the value, and provenance info on these observation nodes. For our stress scenario, we can add new nodes directly on the house price index node and add another set of observations for the new scenario. So that makes it easy to add multiple scenarios, and we still know what house price index we're projecting, and we can easily swap out different scenarios in our query of the data. Okay, so now with our scenarios added to our graph, we can begin to run the predictions in the graph. So one really interesting feature that AnsoGraph has is the ability to add user-defined functions that can be called in a Sparkle query. So what we did was build a TensorFlow prediction function directly in AnsoGraph. The function can leverage AnsoGraph's parallel processing, so we could run projections for each loan in parallel across the cluster. To run the forecast scenarios, we query all of our X variables from the graph to put into the Sparkle prediction function. We also store the trained TensorFlow model in the graph, so we call that in the query as well. The Sparkle function will run the model in parallel across the cluster and then return a predicted state for each loan snapshot. In this example, we predicted that the loan would prepay, so we attached the new predicted state to the loan snapshot, and then we also captured the model that was used to generate the prediction. So this functionality can simplify our execution of the forecast scenarios because we can run the model directly in the graph and significantly improve our model risk management capabilities since we can track exactly which version of the model was used to generate this prediction. So now that we have the predictions in the graph, let's take a look at the data lineage that we captured along the way. So let's look at so we're going to pull up the tool Solidatus. Okay, so Solidatus basically sits on top of our graph database, and it gives us a way to visualize the data lineage that we've captured in the graph. So it allows us to do that through different things. So we have layers, which are these vertical panes here, and then we have objects, which are the boxes, and then we have attributes, which are, in our case, the data elements. So you can see that each layer kind of represents something different. We have the source data that represents our Fannie Mae public data. So these are a couple data sets. We have the FRED API down here, and then maybe some scenario variables that come from the Fed. Then we have our load procedures. So these are Python files or microservices. And then we have our AnsoGraph automated jobs. And then we have a couple of layers for the graph objects. We'll come back to those in just a second. So here on the right, we have at the very end, we have our regulatory report. So let's say, for example, that we want to understand all the dependencies that went into the severely delinquent metric that we're reporting on this template. So what we can do is we can click on this metric and we can do a show trace over here on the left. And what that does is that filters all of our lineage for all the dependencies that went into that. So we can go ahead and trace this back. So we can see that the severely delinquent metric came from our deep neural network prediction. And we can see we have the predicted state data element there. We can see that the training, the deep neural network training that went into that prediction function. And then from there, we can see basically all the X variables that went into the model for training. So if we look at our graph layers, we basically have three layers. We have a core graph objects, And each one of these represents basically a node. And then we have the different attributes that we stored on that node. So we have like a loan snapshot with the snapshot date, a mortgage loan contract, the property, and then the MSA data. Then we have a graph enhancements layer. So for example, we can look at one of the Sparkle queries we talked about earlier, which was calculating the loan age. And we can see that it took as an input the snapshot date from the loan snapshot object, and then the origination date from the mortgage loan contract. So it took those two as an input, and then output loan age as a new attribute on the loan snapshot node. So this just gives us a really easy way to kind of trace our lineage all the way back. Let's look at one more example here. If we'll look at interest rate. So we click on interest rate, we can see it was an input to the model, and then we can see that it came from this load procedure, and it was originally named origination rate. So again, this just gives us a really good way to track our lineage all the way from the reports we generated, through the analytics pipeline back to the source data. Okay, so just got a couple more slides here. So to wrap up, so getting started with a successful POC, we've got just a couple suggestions. So finding a good use case, we talked about some kind of business problems to look for, whether it's combining disparate data sets or finding use cases where you have complex relationships between data elements. Another suggestion is, iterate on building the ontology. So this can kind of seem like a daunting task at the beginning, but if you build it out kind of slowly, get data in the graph, and as you extend FIBO, that's a much easier process. And then finally, showing business value early. And we talked about some of that business value that you can try to show, as early as possible when you're doing a POC. So to recap, the benefits we talked about from using a knowledge graph were reducing time spent on data engineering tasks by using a data model that is more flexible and reusable, capturing data lineage for regulatory compliance, overcoming limitations of machine learning through the use of semantics, enable self-service by connecting business terms to data elements through the use of an ontology, and then finally being able to model complex domain knowledge directly in the graph database. And with that, I'll turn it over to Thomas to talk a little more about AnsoGraph.
Thank you, Greg. Excellent job walking us through that use case. Appreciate that. My name is Thomas Cook, and I'm Director of Sales here at Cambridge Semantics, and I'd like to talk to you briefly about the technology behind the use case that Greg shared with us. Cambridge Semantics was founded on the premise that using graph and semantic ontologies was the best way to handle enterprise data integration at scale. In executing that vision, our founders created the Anso Data Fabric, recently named a leader in the enterprise data fabric category by Forrester Research. In order to be named a leader, you need a world-class, highly scalable data layer that offers incredible performance. And that's exactly what we offer in AnsoGraph DB. AnsoGraph DB is a core component of the Anso Data Fabric, and approximately 2 years ago, we began offering it as a standalone graph database to help with use cases like the one that Greg just walked us through. We even offer a free edition download that can be used for commercial applications. Well, let's take a look at some of the key features of AnsoGraph DB. Direct data access to over 200 sources, including virtualization capabilities. And let's talk performance. We are the fastest graph database on the market today by many measures, one being data load speed. We can load up to 250 gigabytes per hour per node, and that's based on a 32-core vCPU machine, cluster machines. We also support horizontal scaling to trillions of facts to handle data volumes of any size. Hundreds of extensions to Sparkle for feature engineering, geospatial location analytics, linear algebra, and data science functions like PCA and SVD, to name a few. We're built entirely upon standards, which prevent vendor lock-in and promote interoperability. You can see some of our performance benchmarks at the bottom, which are based on industry standard OLAP benchmark called TPC. If you go to the next slide, Greg. The Anzo Data Fabric platform is an integrated platform for delivering and managing knowledge graphs. Anzo's goal is in automating data delivery of data products to data consumers. It gives the users the ability to easily find, connect, and blend analytics-ready data sets with agility, scale, governance, and security. While this presentation is not focused specifically on our products, if you're interested to learn more, we have several other relevant webinars, or we're happy to schedule a meeting to share more information on how we might be able to help you. So with that, I'll hand it over to Mike for the Q&A session.
Great. Thanks, Thomas. And Greg, thank you for all of your insights. And for the audience that's listening, a lot of information has been shared. At the end, I'll cover a recap of how we're going to provide copies of this presentation deck so you can refer to these materials. I'll also be covering how you can get a recording of this along with any of the Q&A. And gentlemen, good news, we do have quite a few good questions here. Let me just start with a starting question. Greg, this would be for you. You had a slide a few minutes ago that said, this is the characteristics of a good starting place. In other words, for the practitioners in the audience, whether they're technical or business, every journey starts with the first step. So if you are in their shoes and you're thinking about a project that would get interest and really leverage the value of graph, what would be the characteristics of that project? One more time, if you could hit that. And then also, if you're walking down the hallways to the executive boardroom and have to have a couple of really compelling reasons to generate the support for business to fund that business case, what would be the one or two things you would definitely include in that presentation?
Yeah, I think that, you know, as we talked about, you know, spending time finding the right use case. So, you know, determining if the business pain points merit the shift from a relational to graph. I think because there is a learning curve, but we've seen that if it's the right use case with the right problems, you know, the knowledge graph can add significant value. So I think some of the ones we touched on were, you know, the cases where you have frequently changing business requirements. You know, that's kind of a big one that we've seen with a lot of the risk analytics projects that we've done. And then I think the other one is, you know, when you try to capture this domain knowledge, we saw a lot of lift from being able to, you know, expose that data. You know, a lot of times it's really complex information that they're trying to model, and it's just much easier to do in an ontology rather than, you know, a relational database, or, you know, producing kind of static documentation that kind of, you know, fades away or is hard to find.
Great. Greg, there are two questions. They have a relationship to each other. One from Apollo in our audience, another one from an Alexander. The one from Apollo, and I'll put them both on the table because you may want to address both of them. There's a relationship. How does the ingestion process work in graph technology with real-time data? How does that get handled? And then Alexander had the follow-up, which is the data ingestion process and the case studies you covered. Was this done automatically? Was this scheduled within the RDMBMS? Were you taking unstructured data? So it's one, the real-time nature of data ingestion and how does graph handle that? And number two, some of the examples you gave, was that done, how was that all that data ingested and what were the different methods?
I'll take, Greg, if you don't mind, I'll take the first part of that question, the real-time ingestion. There weren't any real-time sources ingested in this particular example, but we do support real-time ingestion, Kafka integration, as well as a number of other real-time sources. So we have the ability to schedule jobs, as Greg talked about, a cron mechanism inside of Anzo Graph that can be schedule certain queries. And because we support direct data access to over 200 different sources, you can pull in sources from these different real-time streams and then load those basically in micro batches every 30 seconds or minute or however in intervals of that nature.
Yeah, that's exactly what I was going to say. Yeah, for this, and you know, in a lot of our, you know, in the credit risk space, you know, real-time data, you know, it's not as common. And then, you know, I think to the second point of that question, you know, we found that, yeah, JSON LD makes it really easy to integrate data. that way. So we get a lot of data in JSON format, or we can easily structure it in JSON format. And then, either through, getting it from an API or producing APIs that have this JSON LD, we found that's a really key thing because that, you can dump that into your Ansel graph or your graph database really easily.
Great, thanks, Greg. Here's a question that came in from David, and then another one from Mike. These questions are about, working with ontologies and mapping them to real-world data. The first question from David comes in is, how did you go about the business of taking the industry FIBO ontology, but mapping that to the could be ugly world of production data? And are there challenges, and how do you overcome those challenges?
Yeah, I think that's a really good question. So in our use case, we worked really closely with the enterprise data management team. So it was kind of finding a balance of being able to produce, as I mentioned before, kind of iterating on the ontology. So building the graph, even though the ontology is not perfect, but then going back and being able to refine the terms that are used and tie them back to the enterprise ontology. Yeah, I think it's kind of a balance of using the terms that come directly from FIBO, and then trying your own terms in the actual database, running your process and seeing how that works, and then again going back and refining that process and tying them back to the enterprise terminology or the FIBO terminology.
Great. And Greg, this question comes from Mike, and it's related to the fact that Mike in his question indicates that there's essentially a production version of FIBO and a development version of FIBO that's more of a broader set of still being validated terms. And in the areas of the mortgage loan terms, you were probably working with both the production parts of FIBO and the development parts of FIBO. Anything learned from that process, anything the audience should be aware of in that process of mapping to an industry ontology? And by its nature, since FIBO is open source, it's always continuously being enhanced by members and companies worldwide.
Yeah, I think that yeah, with the development version, yeah, so I think that is challenging because a lot of the terms that we use, like you were saying, from the mortgage loan ontology, were in development. So I think not being so tied to them, but really trying to model what we understand our business process to be, and then finding those FIBO terms to describe it. And so those are going to change, and especially in the development process. So I think really baselining with what our enterprise data management people view as the ontology, how we view the data, the business process, and then trying to link back in and loop in those FIBO terms as they kind of mature.
Great. This question, let me throw it out, which is in the materials you were covering some very specific credit risk scenarios and opportunities. Those are just some of the use cases. So do you mind just giving, for those companies that are financial based, what are some of the more production examples of graph in action that you've seen across multiple companies? In other words, what use cases or business scenarios are getting adoption for graph in the financial markets? And then Thomas, whether you or Greg want to cover, it would be good just to hear. We have many members now joining the council that are retailers, manufacturers. We have new industries joining the council. What are some of the other industry use cases people are thinking of and have applied with success? So Greg, I guess perhaps with you on the, and Thomas to add in, what are the financial use cases that you're seeing a lot of? And this will help, I think, the audience see some good starting points for their projects.
Yeah, I think yeah, we've definitely seen a lot of fraud use cases. So with the graph algorithms that you can use, that's a very good, strong use case. So we've seen a lot of fraud, credit card transaction fraud. We've also seen use cases around operational risk. So just trying to capture broad risks across the organization has been another good one. We've seen a use case with model risk management. So again, trying to monitor your models and how they're being used across the organization. Those are some of the main ones that we've seen.
Good. Thomas, do you want to give the broader other industry perspective?
Yeah, absolutely. We're used very widely in health and life sciences and pharma for clinical trial monitoring and that type of thing. We're also seeing quite a few people doing supply chain, customer experience tracking, customer 360. Fraud is a big use case as well. Network and IT operations is another big area. So it really, knowledge graphs really, span a lot of different use cases and verticals, and we're seeing a lot of manufacturing use cases pop up as well for IoT and real-time integration aspects as well.
Great. And a lot of people might think, Thomas and Greg, that graph is a bleeding edge, brand new technology. But this has been in production, am I right, for many years, and in different industries it has advanced very far. Is that a good perspective, and should someone who is pursuing this as an evangelist in their own company feel good that these kind of technologies have been proven in scale in multiple operating environments?
Yeah, I would say, Cambridge Semantics has been around for over 10 years, and we've developed the ANZO data fabric that is in use at some of the largest health and life sciences and financial services companies in the world, and many manufacturers now as well are beginning to use it. I think one of the challenges to graph was the tooling. There was not a lot of tools, and so it became very difficult to integrate data and to perform queries, connect BI tools. But the ANZO data fabric has solved that problem. And if you're looking to solve enterprise scale problems with a knowledge graph, the ANZO data fabric is a best solution. It provides the integration, the ability to blend and model and visualize, and then create these analytics ready data sets for downstream processing. So we're definitely much further down the road, and I think that's a clear reason why we were named a leader in the Forrester Enterprise Data Fabric report.
Cool. This is a deeper dive question. I'll let one of the two of you take it on, which is, it's from Pornchana, one of our audience members. Can we create a knowledge graph from financial reports in XBRL format? And are there any challenges or points that we should take into consideration?
Yeah, I'm not sure. I'm not familiar with that format. Thomas, I don't know if you have any ideas on that.
I'm not familiar with that acronym either, but I will say that we support both structured and unstructured data, and we have the ability with the ANZO data fabric to connect NLP tooling to convert unstructured data sources or semi-structured sources into the knowledge graph and create triples. And we also work with partners in the NLP space that provide even more advanced capabilities in this area. So that is definitely, many of our customers are processing very large amounts of both unstructured data and combining that with structured data. And that's where the benefit of putting everything in a knowledge graph gives you this holistic view of your enterprise, with the unstructured data being combined with the structured data to give you a consistent universal data access.
Yeah,
and by the way, gentlemen, just a little context. XBRL is a reporting format for financial reporting that's been around in the market. Though I think depending on which circles you're traveling in, it could be deemed as a legacy format, but it's still many reports are reported that way. That might be a good research. We're going to be, as part of the Q&A process, there are more questions than we can ask and have answered on this webinar today. But every question that has been typed in, we're going to be following up with a written response, which gives both the EDM Council and Cambridge time to research a few of these questions and make sure we give the best possible responses. So that'll be happening in the process. There's a really interesting question here. You showed a very interesting data lineage tool, and the question comes also from Alexander. Are the dependencies in the data lineage visualization constructed automatically or semi-automatically? How does that work? Because obviously it was very interesting for the audience to see that.
Yeah, so those were generated, I think you say semi-automatically, because as we showed in one of the examples, we can embed in when we write the code to make the change to like calculate loan age, we can add a piece in there to automatically capture the lineage each time the process is executed. So we've set that up to have, on different kind of parts of the process, you can have these Python decorators that basically sit inside of your code and are sending this metadata to the knowledge graph. The knowledge graph is kind of stringing them together. So there is some setup to it, right? But once you get it set up, you're able to track, runtime. Each run, you're tracking this type of detailed data lineage.
And I also wanted to add, Mike, the ANSO data fabric also gives the ability to track provenance. I mean, this webinar wasn't specifically focused on the ANSO data fabric. We were really just focused on ANSO Graph DB. And so this external tool was used. But if you use the ANSO data fabric and you move data from different places and create these different data layers, transform data that Greg did, that provenance is shown in a similar view inside the ANSO data fabric. So you can track all the different places that the data was transformed to the final resulting data set.
Great, thank you, Thomas. A couple of final concluding questions, and then we're going to share with the audience all of the follow-up that's coming. So just stay tuned for a couple of more minutes, and we'll be sure to wrap up before the top of the hour to let everyone get on with their day. So, gentlemen, you've described some really interesting capabilities, including things like leveraging graph neural networks. Where is this heading? Is there, if you had to set a forward direction of what this will start allowing companies to do, any sort of vision thoughts of the future? Where are we heading, and why should companies make investments into these capabilities? I'm fine if whoever wants to jump on that one first, Thomas or Greg.
Yeah,
go ahead, Greg.
Okay. Yeah, so I think one of the key things I think is seeing that the graph can not only add value to some of this network analysis like fraud use cases, but to also see the benefit in more general data engineering problems like we explored today. And then I think kind of doing all that is kind of setting the foundation for future machine learning and AI capabilities, where you kind of have this feedback loop really tightly integrated with the graph. Right, we talked about some of the knowledge graph embeddings, the graph neural networks, where you can get that really tight relationship between the data and then the machine learning. So that seems to me to be the kind of the future, and being able to build a platform now that will support that type of functionality now and later.
Great, Thomas, anything to add?
Yeah, I would say, one of the other things I didn't mention earlier, the reason why graph, I think the adoption was slow, is that there weren't any scalable solutions out there, right? And we've now solved that problem with ANSO Graph being able to scale to any data volume. And then the user-defined functions that Greg talked about, being able to call the TensorFlow code directly in ANSO Graph, we've developed this user-defined extension capability that allow third parties to write any type of functions that leverage the MPP nature of the database and extend it with C++ or Java. And so we're seeing many different, we use that same mechanism to develop a lot of the capabilities around geospatial and data science and linear algebra capabilities in the database. But we'll see many more partners developing solutions that will make in-graph capabilities possible and give you, these additional functionality to your universe of data.
It sounds, gentlemen, for both of you, exciting. It's a new way of thinking, especially for those that are familiar with the relational world. This is really the next capability that everyone should be thinking about. So a couple of, I guess, the final question, which is key takeaways. One or two, Greg, before we cover some of the key housekeeping items with the audience and wrap up. Any final takeaway, Greg, you'd like to share, and then we'll also allow Thomas to do that.
Yeah, I think the main one is looking for the problems where you need more general data engineering problems, not just the network analysis use cases. Problems where you need a flexible and reusable data model.
Great, Thomas, how about you?
Yeah, I just want to thank the EDM Council and FI Consulting and Greg specifically for this presentation, which really hits squarely on several key points of the value of knowledge graphs. There are clear advantages to relational databases for creating and maintaining analytics-ready data sets. And if you're interested to learn more about Anzo GraphDB or the Anzo Data Fabric, we'd be happy to speak more with you.
Great. Well, gentlemen, thank you, Thomas. Thank you, Greg. Also, thank you to your organizations, Cambridge Semantics and FI Consulting. For our audience, there will be 3 follow-ups coming your way. The webinar platform will automatically generate a recording link that will be sent over the next several hours. So if you just recently joined in or want to pass this on to a colleague in your company or someone outside of your company, we're perfectly fine this gets shared. It's a resource and service to the industry at large. The second follow-up is going to be within a few days. You'll get a second email that will include a copy of this presentation and also all of the Q&A responses. So if you typed a question in, we'll be sure to have a written response. And then third, both Cambridge and also FI Consultant, for those that opted in to receive follow-up communications, they'll be in touch with you with some follow-up opportunities to learn more about their capabilities. And obviously quite a few of those were shared on the discussion today. For learning more, that's a big topic, I think, for everyone on this conference. Some good news about that. The EDM Council has made available as of May this year a 2-day course on open knowledge graph fundamentals with a short overview of FIBO, but we support other industry ontologies like automotive, etc. So if you're either a business or technical person and want in 2 6-hour days to get accredited in the basic core of enterprise architecture for graph, the business case for graph, and do some hands-on work, there's no prerequisite. It's a great way to get that accreditation. Just go to the council website under training and you'll see the details about that. The second is that we are also advocating a shared knowledge graph lab, and both Thomas and Greg covered the AML fraud use case. If you're interested in having your company participate in this lab where we're looking at public data sources and how to leverage them into solving the issues around fraud and AML, just reach out to myself or any of the members of the EDM Council and we'll tell you more about the lab. And then finally, for anyone that would like to join our Data Vision conferences for November 18th, there's a 2-hour member and prospect event. Anyone can join it. You can register right off the website. And that's for the UK EMEA time zone. And for December 2nd, we're doing Data Vision for all of the Americas. And in fact, by the way, Thomas, Cambridge Semantics will be one of the lead speakers there. So we're really excited to hear more about the solution. So with everyone, we're at the top of the hour. Wish everyone a great day. Thank you for joining us. Everyone have a wonderful rest of their day.
Thank you.
Take care, guys.
Bye-bye.